Where's the friction acting?
Between the bottom of the ladder and the ground.
And what's the normal force at that point? Looking for the letter.
Y sub V.
Yeah, that's why it's y sub v. All right, and then for this other equation here, I know that y sub v is equal to the mass of the ladder times g plus the mass of the person times g. So we can figure out what the variables are, everything except for x, just using the forces. So let's put this on Earth 2. Just to simplify some stuff for us. So we end up with 200 newtons for the ladder and 700 for the man. So y sub v is 900 newtons. Therefore, y sub h is 0.6 times that, 540 newtons. So, unless there's a Carroll's error over there. So this is 540 newtons, 540 newtons. This was 200 newtons, 700 newtons, 900 newtons. All right, questions up to here before we actually bring in the rotational stuff. Ourselves a word here. All right, so now we have to take into account, we have to figure out what x is. So we need to bring in a k-hat equation. Well, in order to figure out k-hat, we need to figure out what's our axis of rotation. And there are actually several different points which would all have some convenience to it. Because I know if a force is pointing directly at the axis of rotation, it'd be like being on the end of the door and pushing straight towards the hinge. Or the first thing I did here, where I pushed straight towards the hinge, it's not going to cause that thing to rotate. So any place where the force is pointing directly at it, at the axis, there's no torque from that. And so by carefully choosing our point, our axis of rotation, we can eliminate 2 torques right off the bat. Can't do more than 2. If we pick just some random location, then we would have 5 torques to deal with. So it depends on where you want to, how much you enjoy the math. So, where do you want the axis of rotation to be? And let's see, if I counted right, there are 6 locations which could eliminate 2 torques. Now, let's say that in some situations, there's an obvious axis of rotation. For instance, a door, the hinge just makes sense. But here, we don't have necessarily any place that's gonna rotate about. There's no natural point. What's your gut tell you where to put an axis of rotation here?
Where the ladder contacts the ground.
All right, if we pick that point, neither of these exert any torque, and so we've eliminated two right there. And that's probably the best choice. It also has the advantage of we defined X to be from that point. What is another point that would eliminate two torques? So we got this point right here. That would eliminate two torques.
Well, just based on the fact that that point eliminates two torques, I assume where the ladder contacts the wall.
That would only eliminate one torque, since I don't have any friction here.
Middle of the ladder?
Pardon?
The middle of the ladder?
That would eliminate only one. And so here's the part that students, when they're first faced with this, have trouble sort of jumping towards. The axis of rotation does not actually have to be on the ladder. That could work. That could work. That could work. And then down here at that point, that point. We have 6 points, which will eliminate two of them. But since X is defined from the bottom, that probably makes the most sense. So let's go with that one. So if that's my axis of rotation right here, the question is, which way is the force trying to make it rotate? So we basically have torque from YV plus torque from the friction plus torque from the weight of the ladder plus torque from the normal force from the person plus torque from the wall, or Y sub H, equals 0, just sort of setting up by 5 torques there. I know that's 0 and that's 0, because in both cases R equals 0, RYV is 0, and RF is 0.
What's that first subscript on the top left T, or
That?
down? Yeah,
That's a Y sub V. Or W as I wrote it right there. Y sub V. So what I'm left with, once we eliminate those two, I've got torque from the ladder. Torque from the weight of the ladder would be R hat. Well, R hat is a vector from where we begin to where we hit right here. So I've got R, not R hat, R vector. So I have R going in that direction. This is a 53-degree angle. That would be a length of 5 meters. And my W is pointing straight down, and that is 200 newtons, straight down. So that's my R and my F. It says positive torque or negative torque.
Positive.
How'd you get that?
I know this isn't the right way to say this, but because it's clockwise.
Given our notation here, if something's rotating clockwise,
Right, sorry.
no need to apologize. It is just one of those things that clockwise in a standard setup is negative torque. And the way you could also imagine it seems like you were doing an R cross F. You could also imagine that if this is indeed a pivot point right here, and I applied a force like that, which way would the ladder rotate? Well, the ladder is going to rotate clockwise, which I guess is what he was going with, which into the board, or R cross F here, and in the direction of R, fingers turn towards F, thumb points into the board again. So this R cross F, I got two different ways of doing it. One, I could look at the perpendicular component of this. So that would be R cosine of 53 degrees times 200 newtons negative K hat. So you can just think through it. Once you establish, oh, I know it's going to go into the boards, the negative K hat direction, then I just have to multiply the magnitude of the perpendicular components. Or, if I think about this entire angle here, that entire angle is not 53 degrees, the entire angle is 143 degrees. Negative R, 5 meters, times 200 newtons, times the sine of the actual angle between them, 143 degrees. If I do my math right. Sorry. Yeah. What does this end up being? Given that this is 5 meters.
Negative 601.8.
Meters.
K hat. No, I'm not gonna write K hat up there, because I'm set with all those will be K hats. But technically it is K hat if I'm looking at just the one. All right, so I've got negative 601.8 newtons, Newton meters. Oh, all my units will be the same. So. Plus the person. I don't know where the person is, but what I do know is, well, it's in the same direction as the weight of the ladder. So this number right here changes, and that number right there changes. But my angle is the same. So the torque from the person I know it's going to be in the negative K hat direction. And then it's going to be R hat, which is X. That's our unknown. And then the force is 700 newtons. And then the cosine of 53 degrees or the sine of 143 degrees, whichever one. I'm going to put in the sine, 143 degrees. And so what is 700 times sine of 143? Somewhere around 420.
421. Wait, 3.
X, negative.
said 700 times the sine of 43?
140.
Oh,
The 143. Yeah.
that was just very off, I didn't know why.
And then we are now left with the last one. It's gonna try to rotate it in the other direction, which makes sense. If that's negative and that's negative, we better have a positive if we're gonna add it up to 0. And so we have our force that is to the left. That's our 540 newtons. We have R, which is off at that angle right there, so that's a 53-degree angle. That's my R hat, which is 10 meters at 53 degrees. So I can look at the perpendicular component, sine of 153, or I could calculate that angle right there and do the sine of that. It's the same thing. So torque, because of that horizontal force, positive K hat, because it's trying to rotate it counterclockwise, times 10 meters, times YH, which is 540 newtons, times sine of 53 degrees. Forty-three
4312.
4312.
0.63.
It's now reduced to just a simple algebra problem. Any questions on this before I erase some of it? So it's now reduced down to negative 601.8 minus 421.3x plus 4,312.63 equals 0. Let's see, let's bring that over. So I have 421.3x. And then on that side, somewhere around there.
Should be 8.81.
All right, so we can't, the ladder's gonna slip, no matter how slowly he goes, that ladder's gonna slip before it gets to the top. Suppose we'd gotten a negative value for x, what would that mean?
The ladder would slip even if he wasn't standing on it.
And if we got an x bigger than 10,
It won't slip.
okay. And there it is. I hoped it was everything you dreamed it would be. Questions before we do a non-equilibrium problem? All right. All right, so let's start out with the simple stuff that the chapter 5 stuff. Just simple, let's assume ideal rope, ideal pulley. So the pulley's not gonna turn, it's ideal, so we got this frictional situation going on here, rope's just gonna slip, no loss, infinity. If I do force diagram, let's just work through the facades method here. What are the forces acting on the 5 kilogram mass?
Weight due to gravity.
And tension.
And there's a tension pulling down here, a tension pulling down here. And this one,
Weight.
and
Tension.
it's an ideal rope, so the tension on each side is the same, so I don't have to use the subscript there. Which way will this one accelerate? And this one? All right, so we'll establish those as our positive directions. So the equation of motion for this one,
FT minus W3.
wait, say that again?